It's a great pleasure to be here talking on analysis, especially in honor of Winter Carlson. One of the things that's becoming clear from the talks we've heard so far is what an enormously broad field analysis is. When I taught my first course on analysis to undergraduates, I had to come up with a definition of analysis, and I said analysis was the study of infinite constructions. And I still think this is more or less true. And what I'd like to talk today about is a particular infinite construction called renormalization. And I think it's fair to say that this conference is about perspectives, that renormalization will definitely play an important role in analysis in the coming 100 years. The reason I can confidently say that is that it's a very broad and amorphous topic into which almost any subject can be fit or included. And in fact, I'm going to show you today several different topics that somehow hold together, have a common theme that can be organized around this idea of renormalization. So renormalization really has its strongest roots in physics, especially quantum field theory, but it has many reflections in mathematics, especially in dynamics and geometry, and that's what I'm going to talk about today. So I'm going to focus on four mathematical settings in which renormalization appears. One is the dynamics of quadratic polynomials. The second is the theory of billiards in a plane polygon, and then a discussion of random curves in the plane, and finally some applications to the geometry of three manifolds. So you should keep in mind, though, that there is a underlying physical discussion, which I'm certainly not expert in, but which informs all of these ideas, which is that if you have a complex system, then at the moment of phase transition, say where water is melting or boiling, some sort of universal scaling phenomena tend to arise. So these phase transitions or critical phenomena become self-similar, and the correlation lengths tend to infinity, and one can try to extract some sort of limiting model, which depends very little on the details of the underlying physics. And it's these universal models which are attractive to try to develop mathematically. Okay, so let me first talk about scaling. Scaling is really perhaps the most basic of the infinite constructions in analysis. Maybe it's even really a geometric construction. Certainly the Greeks understood intuitively that if you take a smooth curve in the plane and you focus your attention on a single point, well, of course, we can draw the tangent line to this point. But the modern way to think about this tangent line is the following. If you simply take the picture of this curve under a microscope and you blow it up, so take this ball and redraw it at enormous size, then the curve will look almost straight, and it will be geometrically very close to the tangent line. So the very notion of derivative or tangent line can be thought of as extracting a scaling limit of a smooth curve. You just look at it at a smaller and smaller scale, and it becomes asymptotic geometrically to a line. And this idea is already profitable in the theory of algebraic geometry. For example, if you take a singular point of a curve where it's not smooth, you can try to analyze the singularity by the same kind of process. Here, when you blow up, you would see two lines rather than a single line. And in general, one can define the Zariski tangent cone of an algebraic or even a real singularity as the set of asymptotic secants to the singularity in question. But what it really means is you look at the singularity under a microscope and you see something that's basically a cone over a finite set of points. Okay, so that's a very mild and easy idea of taking a scaling limit. And you'll notice that in the limit you get something that's invariant under scale. The line remains the line as you expand, or this cone remains the same pair of lines under rescaling. Now, let's turn to a more intricate scaling phenomena, but only slightly more intricate, that arises when one studies complex dynamics. So if we consider the complex map, one of the simplest nonlinear dynamical systems, namely the quadratic polynomials z squared plus c, well, what's of interest in the study of these polynomials are the periodic cycles. What happens to points under iteration? And if a point is going to tend toward a periodic cycle, it in particular has to be bounded. So associated to each one of these polynomials, there's a subset of the plane, which is just the set of points whose forward orbits remain bounded. They don't tend off to infinity. And the boundary of this so-called filled Julia set is the Julia set of F. And even for very simple values of C, this filled Julia set can have a very complicated structure. So here's a typical example of a filled Julia set. And one of the things that makes this picture visually attractive is that it has spirals everywhere in it. So for example, if we take this spiraling behavior that we see in the top of the picture, if we were to just, again, look at that spiral under a microscope, what we would see is a much more regular picture. In fact, it's a picture which is almost exactly invariant under rescaling. So here's an example of a fractal object which becomes literally self-similar around many points when you pass to the scaling limit, even though the original dynamical system is highly nonlinear because we have this z squared term here. So that's another example of a scaling limit, and what underlies the existence of this scaling limit is the fact that a complex mapping with a repelling periodic point can be linearized. So let me just say what's going on in this simple example. There's some particular point P which is fixed under the mapping, namely the red dot in the center of the picture. The derivative at this point is of absolute value greater than 1. And these two assumptions already imply that there exists a local coordinate chart W, which vanishes at this point, such that in terms of this local coordinate, f of W is just lambda times W. In other words, this nonlinear mapping can be converted to a linear mapping by a suitable change of coordinate. And this linearized version of the mapping is then exactly invariant under scaling. And so again, we have a sort of scaling limit to this dynamical system. Now, in both of these examples, the scaling limits are rather uninteresting. They're useful tools to be able to talk about this linearization or to talk about the tangent line, but the limit itself is a rather standard and easy to understand object. Now, what brings us much closer to the spirit of the physical theory of renormalization is what I like to call nonlinear linearization. So suppose you have a mapping, and when you look deep into the structure, instead of seeing a linear map like this, you see a nonlinear map. Is there still some way to extract a limiting dynamical system, and what does the shape of that dynamical system look like? So one of the simplest cases, which is sort of a toy model for all of the statistical mechanical pictures of renormalization, is the case of period doubling for real quadratic mappings. Let me write this down in a manner slightly different from what I've written on the slide. Now, for a moment, we're going to think of z as being a real variable. And actually, I like to think of the mapping then as being z squared minus c. A nice way to think about this dynamical system is it's a new kind of financial vehicle where instead of offering to double or triple your money, I take your capital and I square it every year, and then I subtract off a small commission, which is C. So you wisely invest $0 to start out, and then after the first year you're in debt because you owe me your commission, but luckily the square of a negative number is positive. And so the next year you have C squared minus C, and so on. And so you might ask what happens to your initial investment of $0 after it's remained in your account for a long time. So we define the attractor, A sub C, to be the set of limits of f to the n of 0. The possible limiting values of the principal of your investment. And it turns out that what happens is Of course, when the commission is 0, then your account remains statically 0. But as the commission increases, that stable value in your account, well, it slowly moves. It always is an attractor for the dynamical system, but then at some point it bifurcates. And after this bifurcation, what happens is that your balance moves into a cycle of boom and bust. That is, there's a periodic cycle of period 2, and this attractor consists of 2 points. So the long-term evolution is that this sequence of numbers is eventually very close to a periodic sequence of period 2. And then, remarkably, each of those cycles of period 2 also bifurcates, and we obtain a cycle of period 4 when the value of c is larger, period 8 when the period is still larger, and then there is some sort of a phase transition. There's a limiting, very special value of c where the attractor becomes a Cantor set, and for c greater than that value, there's all sorts of turbulent and very interesting and chaotic dynamics happening. And it becomes quite difficult to predict or even describe topologically what the shape of this attractor is. So this is a toy model for a phase transition. We have a sort of stable regime here, an unstable or chaotic regime here, and something very interesting happens right at the phase transition, right at the critical boundary between those two regimes. And what happens there is that you get an attractor of order 2 to the infinity, so to speak, or rather an attractor which is a Cantor set. Now, how can we understand the dynamics on this Cantor set? Well, one thing that's been done experimentally is that many features of this picture have been examined for other dynamical systems. Instead of using z squared plus c, you could replace z with, say, sine of z. And it turns out that you see a very similar picture. And not only that, but the Cantor set you see here has the same Hausdorff dimension as the Cantor set for z squared plus c. The pace of period doublings, you see the period doublings occur more and more rapidly here, is the same independent of the example that we're looking at. That is, there seems to be some sort of universal structure which emerges from this family and which doesn't depend very much on what the formula itself is. And that's the basic idea of one of these scaling limits, at least in dynamics. So how can we try to analyze this scaling limit and develop some sort of explanation for its universality? Well, one thing that's tempting to do when you have this dynamical system with very high period, with period 2 to the infinity, is to try to accelerate the dynamics. And this is the other feature that really needs to be introduced to achieve renormalization proper. Not only do we need scaling, but we need some idea of acceleration. And the idea of acceleration is very simple in this instance. In the limit, we have some sort of a mapping which preserves a Cantor set. So I'll draw the Cantor set schematically as a nested sequence of intervals, each being cut in half. And what the mapping does is the first iterate interchanges the two largest intervals in this description of the Cantor set. So if we want to make the dynamics go faster, what we can do is we can take one half of the Cantor set and just consider the second iterate of the mapping restricted to this half of the Cantor set, or to the subinterval containing that half Cantor set. And this new accelerated mapping is called the renormalization of f. Now, of course, the renormalization lives on a smaller interval than the one we started with. So if we want to iterate this process, this interval will shrink down to 0. It'll approach a point in the Cantor set. So what we really need to do is rescale. And then the remarkable fact, which has emerged over several decades of study, but experimentally and finally conceptually mathematically, is that if you take this limiting, very special mapping with the Cantor set attractor, you take its second iterate and keep rescaling, that is, you keep accelerating the mapping, then it tends to some sort of universal analytic dynamical system, which has the property that it's equal to its second iterate. So let me just draw you a picture of what happens, what the limit of renormalization is here. From that simple polynomial, we obtain in the limit some complicated mapping with infinitely many folds defined on the entire real line with the property that it is literally equal to its second iterate under rescaling. And this is what I call nonlinear linearization. That is, here's a mapping which is literally similar to its second iterate. The original mapping is only approximately similar to its renormalization. And here that similarity becomes exact. This is called the fixed point of renormalization. Okay, so let me just say a word about what's known about this process of renormalization and the developments over the past couple of decades. Namely, well, this renormalization was first discovered by Feigenbaum and Collett and Tresser, and they offered a physical explanation for the phenomena, which I'll come to in a moment. Then it was developed by Lanford and many others. There were rigorous proofs of many aspects of renormalization, but I think the real architect of the final theory that has emerged was Dennis Sullivan. He built a framework in which this renormalization picture could have a final rigorous conceptual explanation, and after the work of many additional people, this was put on achieved a final form with the work of Lubitsch, and the final form is in fact exactly as conjectured by Feigenbaum and Collett-Tresser, but it's a little bit more mathematically rigorous, and the final form looks something like this. Well, you see, once you take a quadratic map and you take its second iterate, you have a polynomial of degree 4. You renormalize again, you have a polynomial of degree 8. So as you renormalize, you're moving out of the realm of polynomials into some general realm of analytic mappings. So one of the big problems in defining renormalization is to find the right space of maps in which to work. And this is now called the space of quadratic-like maps. And of course, although the discussion has been defined over the real numbers, everything can be made to proceed over the complex numbers. And this is really the key to the conceptual understanding, is to work in a holomorphic setting. And then it turns out that the fixed point for renormalization, the exotic mapping which shown on the screen, is in fact a hyperbolic fixed point for the operation of renormalization on this entire space. So the renormalization operator proceeds on the space of all suitable functions. This mapping that's drawn, the fixed point is obviously invariant, and then it turns out it's a hyperbolic fixed point with a codimension 1 stable manifold and a dimension 1 unstable manifold. And so what happens is that to construct this fixed point, what we did is we started with the family of quadratic polynomials. And in this family, we saw this cascade of period doublings and then finally a Cantor set. What that Cantor set attractor was telling us was that this was the exact point at which the space of polynomials of degree 2 crossed the stable manifold for renormalization. And so starting with that very special quadratic polynomial, under iterated renormalization, we converge to this universal fixed point. If we had started with a slightly different polynomial, slightly past or before the tip of the cascade of period doublings, it would have simply gone off to infinity under iterated renormalization. So this is a characteristic property. To get this scaling limit, one has to be at the point of phase transition, which corresponds to the Cantor set attractor in our setting. Okay. Let me just say a word about how this picture finally resolved many of the questions that or justified many of the observations of physicists, and then what the main method was. Because of this hyperbolic nature of this fixed point, all of the geometry taking place at this fixed point is reflected in the geometry of the space of polynomials of degree 2. In particular, the pace of period doubling is nothing more than the expanding eigenvalue of this operator at the fixed point. So it gives a very clear understanding of why all sorts of different families have the same universal behavior. All of those families are simply reflecting the behavior of this unique scaling limit. And the second thing that's important is, where does this hyperbolicity come from? That's perhaps the most mysterious question from the point of view of physics and dynamics. And from the point of view of analysis, it has an absolutely beautiful answer. Namely, there is really only one source of contraction in analysis. It's the Schwarz lemma. And in fact, the contraction here comes from the Schwarz lemma. There is a complex structure on the stable manifold, and if we take a ball around the fixed point, it's mapped properly inside of itself with one iterate. So the hyperbolic metric on this ball is contracted, and therefore we have all of the eigenvalues of the renormalization operator strictly inside the circle on that stable manifold. Okay, so this is a beautiful discussion of how complex analysis intervenes in giving a conceptual explanation for this instance of renormalization. I'd like to mention a couple other instances in the quadratic family before proceeding to more general dynamical systems. So one other instance of renormalization that's very attractive is the analysis of circle mappings. So suppose we have a mapping of the circle to itself, say a diffeomorphism. And it's been known for a long time that if this mapping is smooth enough, then it's conjugate to a rotation. So it's topologically the same as a rotation by angle theta, which is called the rotation number of f. But it might not be smoothly conjugate to a rotation. So we can try to analyze the more detailed structure of these mappings of the circle. And one way to do that is to start iterating a point around the circle and wait until it comes back close to itself again. And then there's a small interval on the circle where the first return map is represented by a high iterate of our mapping f. And so again, we can accelerate the dynamical system by waiting for it to come back to this smaller interval. So we take this interval here, we glue its endpoints together to make a small circle, and then we take the induced dynamical system Fn, and then of course we rescale it, so it becomes a large circle again, and this is the renormalization of f. It's f to the n restricted to L rescaled. Now you might wonder how the rotation number for the renormalized mapping is related to the rotation number for the mapping you started with. And it turns out to be related by the transformation that theta goes to 1 over theta. So this, I think, is a beautiful instance where you start to see that renormalization involves some other classical mathematical discussions. And as soon as a mathematician sees the transformation theta goes to 1 over theta, they have to think to themselves, SL2Z. Because this is one of the Mobius transformations for SL2Z acting on the upper half plane. If we have the other transformation, say theta goes to theta plus 1, that doesn't really change the rotation if the total length of the circle is 1. These two transformations together generate the group SL2Z and bring this group into play in the study of these dynamical systems. So let me just mention how one can conceptualize the intervention of this group SL2Z and just quote a typical result that can be proved by using this perspective on rotation mappings. So here's a somewhat more conceptual way to see where SL2Z comes from when you study a map of a circle to itself. What's the good geometrical way to think about a map of a circle to itself? Well, to get a geometrical model for the dynamics, what you can do is you take a cylinder, that is the circle across the interval here at the bottom, and then you use the dynamics to glue one end of the cylinder to the other. You glue x on one end to f of x on the other end. And the result when you do that is that the straight lines foliating the cylinder horizontally here wrap up to become a foliation of a torus after you've done this gluing. And the great thing about this torus picture is that now time and space are on an equal footing. The time direction is the direction of the foliation, the space direction is the circle direction. You've combined both of those directions into a single two-dimensional space. Now the original dynamical system is recovered by just drawing a transversal to this foliation, a loop on the torus, And if you draw loops in different directions, you get different induced dynamical systems on the circle, which are all essentially equivalent to the one that you started with. So the group SL2Z really intervenes as the symmetry group of this two-dimensional torus, where you've mixed up time and space, and each of the elements of SL2Z gives you a different way of looking at your original dynamical system, a different way of renormalizing your circle map. So let me just mention a beautiful theorem of Yoko's that was proved using this philosophy. And this is also related to quadratic mappings. Namely, one can consider the mappings f of z of the form e to the 2 pi I theta z plus z squared. These are the simplest nonlinear versions of irrational rotations. Without this term here, if theta is not rational, this mapping is just an irrational rotation, leaving invariant all the circles in the plane. What if we make this mapping slightly nonlinear? Is it still possible to linearize it? That is, change coordinates so that it is, in fact, analytically conjugate to its linear part, this rotation, near the origin. And the beautiful theorem developed by many people, say Ziegel and Bruno, but put into a final form by Yoko's, is that there is an exact condition on theta such that this mapping can be linearized. And what I want to emphasize about that condition is that it is invariant under renormalization. So theta can be linearized if and only if its renormalization, 1 over theta, can be linearized. This is another way of saying that the condition for a rotation number to be linearized only depends on the tail of its continued fraction expansion. But in formulating it this way, what we're saying conceptually is simply that the set of linearizable germs is closed under renormalization. And indeed, the idea of renormalizing the germs via a complexification of the construction I've drawn here is what underlies Yoko's proof of this theorem on linearization. Okay, so that's another instance of renormalization in the setting of dynamics. Now, as long as we're discussing irrational rotations, I want to move back closer to physics, towards classical mechanics this time, and say something briefly about area-preserving maps. So there's another setting in which irrational rotations have been abundantly studied in dynamics, namely the Kolmogorov-Arnold-Moser theory, or KAM theory. And this theory contributes a lot to our understanding of area-preserving maps. So let me just say what's in this picture and what it says about our current state of knowledge. So what's happening in this picture is, this is a picture of a sphere, and on this sphere there's an area-preserving transformation, and we're drawing orbits of this transformation. Now it turns out that this transformation has elliptic fixed points in the centers of these islands that we see here, and near those elliptic fixed points, the orbits are moving around smooth invariant circles. So there's a lot of very nearly periodic or elliptic behavior in this picture. And this is exactly what the KAM theorem predicts. It says that if you have a mapping which is area preserving and the derivative is a rotation, then nearby you expect to find a positive measure set of orbits which are actually just circulating around circles. In particular, the dynamics can't be very wild. It can't be ergodic, because these orbits that start near in one of these islands are trapped in that island for all future time. But that's not the whole story. As you can see, these islands go through their own bifurcations. This island here, for example, is surrounded by 5 other islands, which are moving around with a rotation number of 2/5 or so. And though there's other smaller island chains here, so there is some kind of bifurcation sequence going on as you reach the boundary of these islands, which cries out to be studied by renormalization. But even more striking, I think, is this region in here. This is what the mathematical physicists call the stochastic sea. It intervenes between the elliptic islands. And what this black region is actually just the orbit of a single point. So there's a single point which appears to move around ergodically on a set of positive measure that intervenes between all of these elliptic islands. And almost nothing is known about this stochastic sea. So I don't think there's a single real-life example, that is one that's not specifically contrived, where one can show that this stochastic sea actually exists, that there is a positive measure set which is not involved in the elliptic islands. So in some sense, the theory of irrational rotations, beautiful as it is, only reaches out so far in our study of area-preserving maps, and this stochastic sea is really our sea of ignorance. There's a huge amount of experimentally clear and yet mathematically unjustified statements one can make about area-preserving maps. Now, why are area-preserving maps so important? Well, in classical mechanics, there's a symplectic form on phase space. So when Poincare set out to analyze the three-body problem, he proposed the idea of taking a cross-section to the set of configurations of the planets, waiting till they come back near their original position, and seeing what the induced transformation is on that cross-section. Well, since there's a symplectic form preserved on the total space in the classical Hamiltonian dynamics, on this cross-section, you obtain an area-preserving transformations. So these are the transformations of most interest in conservative systems, in, for example, celestial mechanics. And it's amazing that even 100 years since Poincare started looking at them, some of the most basic phenomena are still very poorly understood. Okay, so what do mathematicians do when they don't understand something, when they find a simpler model that they also don't understand? So let me pass to a yet simpler classical mechanical system, namely billiards. And maybe I'll begin with billiards in a square, since this can be analyzed. So if we look at the motion of a particle in a square under reflection off the sides of the square, well, this is something that you can pretty much figure out. You can analyze what happens to trajectories. And the way to do it, well, let me first say what the statement is and then the method of analysis. If you look at the motion of a billiard particle in the square, it turns out that there's really only two possibilities. Either this particle is moving at a slope theta, well, let me call it a slope, s. Either the slope s is rational, and if the slope is rational, then the particle will return to where it started after a finite number of bounces, so we get a periodic trajectory. Or the slope is irrational, in which case the particle is not periodic, but even worse, it's uniformly distributed. It goes everywhere in the billiard table. So what that means is that if you start with an irrational slope and you fix a region in the table, then the amount of time that the trajectory spends passing through that region is proportional to the relative area of that region to the area of the whole square. So it goes everywhere in the square and it doesn't favor any one region over another. Okay, so this is a beautiful basic dichotomy that obtains for billiards in the square, and you could ask for more general polygons what happens. So for example, what happens with billiards in a pentagon? So here's a picture of a long billiard path in a pentagon. It doesn't appear to be periodic. Is it in fact evenly distributed in this pentagonal region? Okay, so let me give you a warning before we proceed to the theory. It's not always true when you go to more complicated billiard tables that there is this sharp dichotomy between periodicity and uniform distribution. So here's an example of a billiard that started out in a square, but then I added a little addition to the square, this rectangle that's been tacked onto the top. So this billiard would have just been completely periodic, except for the fact that we opened this little corner for it to occasionally make excursions into. And what happens is that the billiard now is completely aperiodic. It moves around densely in the region that's drawn here, but it never visits the two corners of this billiard table. So it's not a periodic trajectory, and it's also not uniformly distributed. So this shows that when one goes to more complicated billiard tables, one can't expect to have this sharp organization between periodic behavior and uniformly distributed behavior. Okay, now how can one go about analyzing billiards? Well, again, this idea of acceleration is very useful. So let me say a little bit about how it works in the case of a square table. In the case of a square table, what you can do is you can build from the square table, again, a torus. This torus is really built by taking 4 copies of the table, laying them down one next to each other, and then observing that you can just let the trajectory pass from one table to an adjacent table by moving in a straight line rather than by reflection. So if you assemble 4 copies of the original square and glue them together, then the original billiard motion becomes nothing more than the geodesic motion on a flat torus. And that reduces the theorem that we've quoted to the familiar result that on a flat torus, any geodesic is either a closed geodesic or it's uniformly distributed on the flat torus. What happens when you take an L-shaped table, like the one that's drawn there? Well, here, again, you should take 4 copies of the table so that the billiard motion can be reduced to motion along straight lines. And then you glue together corresponding edges of the table that you've developed in this way. And now the billiard flow becomes the flow by straight lines in this shape that might be called the Swiss cross. But the Swiss cross folds up now not to give a torus, but to give a surface of genus 2. So we have a surface of genus 2 with a certain singular metric on it, such that straight lines in this metric correspond to billiard paths in the L-shaped table. Okay, now notice that this surface of genus 2, like the torus, it comes equipped with a complex structure. It has charts in the complex plane, just coming from the original charts from the table. So you can think of this as a Riemann surface X. And now what we want to do is renormalize. If we want to understand the long-term behavior of the billiard flow, what we want to do is make the billiard flow go faster. So I don't want to have to wait for this trajectory to go all the way across the square. How can I make it go faster? Well, I'll just take that trajectory and I'll shrink its length. That is, if we fix a slope for the billiard flow, it gives the foliation of our surface, and then we can take that foliation and we can shrink the leaves of the foliation, make them shorter, and at the same time compensate by expanding in the orthogonal direction. That is, make space longer and make time shorter while keeping the total area of the surface fixed. And that defines a family of Riemann surfaces depending on a parameter t, t describing how quickly we shrink the lengths of these geodesics. So let me just state now a basic theorem which uses this beautiful Riemann surface picture and this acceleration or renormalization to analyze the dynamics of the original billiard. This is a theorem due to Howie Mazur. And it's really the basic technique now for studying dynamics of billiards in tables with rational angles. And it says that the billiard flow is uniformly distributed if this sequence of Riemann surfaces xt is recurrent in the moduli space of all Riemann surfaces of genus G. So this moduli space is some non-compact but finite dimensional manifold. This renormalization flow defines a family of Riemann surfaces moving around in that manifold. If that family returns infinitely off into a compact set, then we get this good conclusion here that we have uniform distribution of those trajectories. So let me just quickly summarize what's known. In fact, using this theorem of Mazur's, it's now known that billiards in the regular n-gon do obey this dichotomy. That is, for any slope, you either have a periodic trajectory or it's uniformly distributed. So they are, so to speak, good tables. There's a small but growing list of good tables, and one of them is the regular n-gon. This was proved by Veitch. And the second recently discovered family of them, which I'll just mention, are L-shaped tables with the following parameters, where gamma is 1/2, 1 plus the square root of d. D is a rational number. So just a word about how these billiard tables are analyzed. You have some sort of path in the moduli space of all Riemann surfaces. You want to understand the dynamics of this path. Well, in fact, for these good tables, you can always show that this path, in fact, lies on an algebraic curve in the projective variety of all Riemann surfaces of a given genus. And by confining the path to an algebraic curve, it becomes much simpler to analyze its recurrence properties. In fact, it's almost always recurrent unless it goes out a cusp of the curve, but that turns out to correspond exactly to these periodic trajectories. So just in one word, the end of the story is the way all these things are proved are by showing these tables actually correspond to algebraic curves on the moduli space of Riemann surfaces of genus G. I find this a really beautiful story because you start with one of the most naive questions you can imagine in classical dynamics, and the next thing you know, you get to do complex analysis. Okay. So, from the last two topics, I want to move from classical mechanics to statistical mechanics, where scaling limits are also extremely important. So let me first remind you of one of the most beautiful statistical mechanical systems, Brownian motion. So let's see, suppose you want to construct a random path in the plane. Well, one way to do it is you divide the plane into a very fine grid, and then you let your collaborator take a drunken walk on that grid. That is, at every moment they choose at random one of the 4 possible directions in which to move. And a typical drunken walk looks like what I've drawn here. It starts at this red point. It retraces itself rather often, and it ends up at this green point here. So this is a beautiful process which, under rescaling, as we know, converges to Brownian motion. It's related to Laplace's equation and diffusion. And there's a beautiful link between this discrete process and the corresponding limiting continuous process. So from Brownian motion, or rather from the scaling limit of random walks, I should say, we obtain a method for drawing random curves in the plane. Now, the problem with this method for many applications is that these curves run into themselves all the time. And there are lots of situations where you would like to have a model for random curves in the plane which are simple, which do not cross themselves. And it's been quite a challenge for many years to give a reasonable construction of a random simple closed curve in the plane. It's not that hard to give combinatorial constructions, and I'll give you one in a moment, but what is hard is to give a continuous construction, a construction of a fractal curve which doesn't cross itself. And that's because, of course, such a curve can't be constructed by a local procedure because it has to know to avoid the portion of the curve that's been drawn so far. So let me tell you the remarkable solution to this problem of constructing random simple closed curves proposed by Oda and Schramm. This is called SLE kappa. It's mentioned already in Peter Jones' talk. The idea is the following. If we want to construct a random curve, let's say it's moving from the boundary of the unit circle towards the center of the disk. One way to do it is to think about these curves in terms of the Riemann mappings. So for each time t, there is a unique Riemann mapping, f sub t, that sends the disk to the disk with this slit removed. And if we parameterize the path correctly, then we can normalize this mapping so its derivative at the origin is just e to the minus t. So then we get associated to this path a family of Riemann mappings, and not only that, but the tip of the path is described by some point on the boundary of the circle in the domain of the Riemann mapping. This point is more or less measuring the apparent angle of the tip of the path as seen conformally from the origin here, as seen along hyperbolic geodesics in the complementary domain. Okay, now here's the brilliant idea of the definition of a random path, namely, you choose this path so that this point, W of t, undergoes Brownian motion. So SLEK is defined to be the random paths gamma of t such that W of t is equal to Brownian motion with time parameter t scaled by kappa. So for example, if kappa is 0, then the point W of t doesn't move at all, and we just get straight lines, geodesics joining, radii joining the boundary of the disk at random towards the origin. But as we increase the value of kappa, these lines become more fractal, and it's a basic theorem due to Rode and Schramm that in fact this gamma is a simple closed curve for kappa in the interval from 0 to 4. Okay, so this is a synthetic construction of a simple closed curve using, in fact, a whole family of simple closed curves using the Riemann mapping. Now, how else can you construct simple closed curves? Well, here's another procedure in the spirit of random walks. It's a combinatorial procedure rather than an analytic one to construct an approximate random path. And in this discussion, what you ask your collaborator to do is the following. They take the drunkard's walk as before, but now whenever they come back to a place they've been before, they forget that portion of their random walk. They remove that loop and then continue on again. So we're trying to construct a simple curve, a simple path. If we come back to a site we've visited already, then we erase this part of the path. We just forget that. That's called loop erasure. And then we continue walking. Maybe we create another loop. We forget that, and so on. So this procedure is called loop erased random walk. And of course, by definition, it constructs a simple closed curve in the plane. So this is one of the many combinatorial procedures proposed for constructing simple random walks. And it begs the question, what happens as you rescale? What happens as you renormalize and make the lattice finer and finer? Is there some sort of scaling limit of these stochastic processes? And the remarkable fact, which is due to Lawler, Schramm, Werner, and also I think was in many ways presaged by the work of Richard Kenyon, is that in fact loop erased random walk converges under rescaling to this process SLE2. So in fact, just as Brownian motion exists as a limit of ordinary random walk, this combinatorial procedure converges to this SLE process. And what that shows after the fact is that in fact this loop erased random walk process is conformally invariant. It's very insensitive to the way in which you rescale the lattice or the shape of the lattice. If you take two regions which are related by a Riemann mapping, the way you discretize them is completely different, but the way you form these limits is exactly the same. Okay, so I'm almost out of time, so I think in the remaining 2 minutes, I should just talk about one last instance of renormalization, namely the proof of the Poincare conjecture. So the final example of renormalization, and I'll try to say most of this without writing, is the Ricci flow on the space of metrics on a manifold. This was introduced by Hamilton about 20 years ago. So I've written the differential equation for the Ricci flow up here. But roughly speaking, what this equation does is it starts with a metrized Riemannian manifold, and it changes the metric by shrinking the metric in the places where the Ricci curvature is positive and by expanding it in the places where the Ricci curvature is negative. So I've drawn a sort of schematic picture of what it might do to a surface that's embedded in 3 space. And well, first, why should this be considered an instance of renormalization? Well, first, this is a sort of a scaling limit of a discrete process. The process here is you want to change the metric at a point on the manifold so you can average the metric over nearby points to try to define a new metric at this point. Put differently, the Ricci curvature is in fact equal to minus 1/3 the Laplacian of the metric when you work in geodesic coordinates at a point. And so in fact, at each point working in the tangent space or in exponential coordinates, this equation we've written down here is just the heat equation with the Laplacian of the metric playing the role of the evolution parameter. So that's one reason in which it's like renormalization. Another reason is that if you start with a round sphere and you apply this flow to it, what will happen is that the sphere will just shrink to a point in a finite amount of time. So if you want to keep seeing the manifold, you have to keep expanding it. So there's definitely a rescaling process which is necessary in carrying out this flow for infinite time. And finally, there's a very sophisticated reason that the Ricci flow is like renormalization, namely that physicists like Dan Friedan and his coworkers have analyzed the renormalization of string theory, where the target is a Riemannian manifold MG. And in physicists' view of renormalization, you're allowed to change all of the parameters in the system simultaneously. In particular, you're allowed to change the metric on the target manifold. And for their renormalization flow, the metric evolves according to the Ricci flow. So that's another reason that this is like the renormalization we've discussed before. Also, physicists are very happy with this because the stationary points correspond to Ricci flat manifolds, which are the solutions to the Einstein equation for vacuum gravity. Okay, so just in 2 words, what's the upshot of why am I bringing the Ricci flow in? Well, of course, it's because there's recently been some announcements about progress on one of the big problems of the past 100 years. So just to put this in context, let me say that at the turn of the 20th century, one of the central concerns of analysts was the following 2-dimensional question. If you have a Riemann surface X, is it conformally isomorphic to the quotient of the upper half plane by a discrete group? And many people, including Poincare, made contributions to the uniformization theorem, which was finally proved by Kuba and others. So this was sort of the 20th century question. Well, at the turn of the 21st century, we're working in 1 dimension higher, and one of the central questions is, if you have a 3-manifold, is it usually diffeomorphic to a quotient of hyperbolic 3 space by the action of a discrete group? And by the way, it doesn't always have to be isomorphic to hyperbolic 3 space. It could be isomorphic to a 3-sphere or another list of exceptional manifolds, but this would be the typical case. Well, Hamilton proposed a program for solving this 21st century uniformization problem by using the Ricci flow, and recently Perlman has made some breakthroughs which make it look much more plausible than before that this program will actually succeed. And I just think it would be a remarkable turn of events if the 20th century opened with Fourier's theory of the mechanics of heat intervening to resolve one of the main problems in topology by an analytic method. So I'll stop there. So it's not clear whether or not it will be approved, and I certainly don't want to weigh in on one side or the other, but I would say that for a long time it looked implausible that such a local equation could solve these kind of global topological problems, and now it looks much more reasonable that this could actually work.